Thank you for joining my talk on robust perception for autonomous systems. Today I will focus particularly on autonomous driving. This is what we imagine when we think about autonomous driving. A smart car with dry humor, driving safely in the most crazy driving situations. The reality is more like this. Even in simple scenarios such as parking assistance, our autonomy might fail. In this case, it's just a small bump. At higher speeds, failure of autonomy software can be much more dangerous. This type of failure can cost human lives or at least result in dangerous injuries. So, what is it that makes it so hard? Some people say it's just engineering challenges and we can iron them out by better engineering. Today, I will argue that this is not the case and look at some of the basic research challenges behind autonomy. First of all, I will look on what we can do when maps are not useful anymore and we cannot rely on SLAM systems. And second, I will discuss on how we can use perception to improve our learning and control systems. So, what do we mean by SLAM and SLAM becoming not useful? Let's quickly take a look first at classical SLAM approaches. Classical SLAM approaches use a variety of sensors. The ones I've been working on were inspired by the human navigation system. Humans use two organs, obviously the eyes, and the inner ear organ for inertial cues. And the sensors that we used for SLAM were mimicking just that. It were visual inertial sensor systems that contain stereo cameras and inertial measurement units. A popular combination these days for localization and mapping. And a lot of work went into tuning and designing such systems, their calibrations, and things like that. SLAM systems that are based on this type of sensors usually perform in a variety of ways. The flavor we've been usually looking at detects some key points in an image, then it subsequently tracks these key points over a period of time and ultimately uses this information to build a 3D model of the environment. The 3D model not only contains the key points, but it also creates a descriptor for each key point. These descriptors are used as a description of the area around them, and it's a major challenge to make them right. Because on the one hand, we want each descriptor to be very distinctive, to differ from descriptors of other key points. And on the other hand, we don't want the descriptor to change too much under small appearance and viewpoint changes. So we store all these descriptors in a big map storage, and localization becomes then a big retrieval task, where all the observed descriptors are matched to the descriptors in the storage, and then some geometric consistency check is performed. So we were interested to look at such maps during appearance and structure changes, and what we can do to address those changes and to make the maps robust. And this motivated the development of a multi-session mapping framework called Maplab. Here you see a set of maps generated from Maplab of the entire Zurich inner city. When we decided to develop Maplab, there were already excellent frameworks for mapping backends, great optimizers that we could use. But what was missing is a framework for a mapping front end that allowed to record, process, and manipulate multiple maps. The two main components of Maplab are a MapLab console, a console for map manipulation tools, and Rovioli, an extension of the Rovio framework that basically allows us to localize from maps stored in MapLab. And all of this is available online and can be used for your own mapping research. So, using of MapLab allowed us to consider a big variety of use cases. Here you see the map creation at ETH where we created several maps running through ETH corridors and then aligning these maps to each other. We also allowed to interface 3D reconstruction tools and create broader maps, such as the one you have seen in the beginning of the inner city of Zurich. What you see nicely also in this video is how creating these maps is challenging. For example, in the corridors, many features look alike, and in both environments, indoor and outdoor, appearance of structures may change strongly, or certain things might disappear that have just been present a short time ago. So maps may become outdated. So a lot of the work focused on research on better maps. For example, choosing particularly useful key points, those that are more likely to be persistent over a longer period of time and to appear similar over this period of time. We have been doing an early work in that space where we learned a robustness classifier for key points. Another line of research looked at evaluating the quality of maps for localization and visualizing this quality. So, as said, we focused on building better maps, and since then, numerous other works have addressed this particular challenge on how we can build better maps, what is a good way to store maps, to compress the stored maps, and so on. The question I faced as I started to work more and more on autonomous vehicles is whether it is actually enough to build better maps if we want to achieve localization at scale. Will it be enough to have these maps and to allow us for human-level navigation? And soon we found cases that actually pushed to the limits of classical localization systems. So, for example, certain driving scenarios where mapping seemed infeasible the way we were doing it before. So we started to look at approaches that went beyond 3D maps. So here you see such a scenario. On a road like this, there are at least two challenges for classical mapping systems. First, perceptual aliasing. A lot of features that we would extract here look alike, even with slightly different types of features or slightly different types of SLAM that uses maybe other slightly different sensor types such as LiDAR. These challenges would still persist. On the other hand, this environment is prone to very strong appearance changes between summer and winter. So while driving here a few months later, you would see a completely different image. For humans, this is not a problem at all. We can easily drive here. But mapping systems reach their limit. We were wondering, is precise localization even needed if we want to drive safely? That's not how we humans drive, after all. And several works in the past have motivated this thinking. Some of them used OpenStreetMap for localization. Sometimes it's just incorporating building information, which is not possible in the example above. The work probably closest to us has been done by Ruchtier et al. In Wolfram Burgard's group, where road segmentation has been used for localizing from OpenStreetMap data. In our work, we are not really interested in being perfectly localized all the time, as long as all location-specific decisions, such as taking turns, are made right. So in these critical situations, for example at intersections, we need insufficient localization to take the right turn. We don't need more. And this type of research became very popular and has been also approached from the opposite direction that tried to reduce the data stored in maps. A recent work from the group of Rachel at Uber focused on creating maps that do not contain high-definition 3D models, but simply focus on storing lane information and information about street signs. So they simply use different data types and massively reduce the data requirements of maps. Our idea was, why localize at all? Humans, as mentioned, don't drive at centimeter level using centimeter level global localization. So can we mimic human driving by looking at similar types of maps and only staying robustly on the road? To this end, we took our classical driving pipeline that is very similar in most autonomous driving systems, and we modified this pipeline. The most important modifications being adding a road segmentation and a map warping module. And as a result, we were able to robustly navigate without 3D maps. Here you see our testing and evaluation done by Teddy, who was leading this research, on our Devon's testing site. It's an outdoor testing environment where we can do a lot of fun things and try out autonomous driving algorithms without any obstacles, as we can simply reserve it. And the interesting thing to see here is that the system relies merely on proper road segmentation and is able to navigate safely from one starting point to a given goal point in an OpenStreetMaps map. So this system that we have seen just now might have a hard time in an environment like this, because in an environment like this, road segmentation might fail or be at least very hard. And still, humans can still drive in an environment like this. Admittedly, even humans do more mistakes in such environments. It is very challenging after all. And we also have to drive much slower to avoid obstacles because the visibility is also much worse for us. But if we stick to these rules, if we use common sense, if we drive slower, we actually can traverse this route safely, even with very few environmental features. We are very good at capturing these few features and knowing where we are. And this is something that is still very challenging for classical perception algorithms. So our work was to mimic that capability of humans by using a ground-penetrating radar. Here you can see it, a prototype. And of course, because it is a prototype, it is somewhat bulky, but a product version does not have to be that bulky. The basic concept of a ground-penetrating radar has been developed at MIT Lincoln Labs over 5 years ago regarding the use of localization. And it has been used in geosciences for much longer to analyze soil structure. And additionally to us, today there are several companies looking into further developing this concept for autonomous driving research. Here is an example of how LGPR data looks like. We basically look at the soil structure under the vehicle and create a scan of that structure. And then we can perform localization based on scan matching. Our first interest was, of course, cross-weather localization and integration of this type of sensor in an autonomous driving stack. Here you see Teddy again testing the ground-penetrating radar in a Boston winter day. The interesting thing about this test is that he uses a map that has been recorded under different weather conditions, and we show in our work that localizing across different weather conditions is possible using a ground-penetrating radar. And the interesting and exciting thing is localization may not be perfect, but we merely use scan matching. So there is a lot of room for further research and for improving the way this system localizes by taking inspiration from existing SLAM research. So when we speak about perception for autonomous driving, we often think about problems such as SLAM shown here, or other perception problems such as object detection, segmentation, or reconstruction. But better perception can also help us to derive better decision and control policies. The key idea here is to use simulators based on real-world data and thus leverage the perception research for things such as learning end-to-end control policies. Why is this relevant? So if we want to use machine learning for learning driving policies, we need a diverse set of scenarios for training a neural network to drive robustly on the road. But even validation of classical pipelines requires complicated edge cases to be present in the data, which in turn requires very experienced human drivers. So most datasets don't have any of these. Our idea was to use real-world data to build a simulator and then to allow agents to navigate autonomously within the simulated environment. There has been a bunch of work using simulators for learning driving policies. Some of them purely use a model-based simulator, which is model-based simulators, which are hard to transfer to real world. Other approaches try to achieve this transfer by explicitly developing domain transfer methods and training domain transfer policies, or using other approaches such as domain randomization. More recently, a new type of approaches emerged that is based on photorealistic simulation using some sort of 3D reconstruction. In our case, we don't want to use 3D reconstruction because the environments we are going to simulate are huge. Instead, we are interested in simply performing local reconstructions, not requiring the full environment to be reconstructed for the simulation task. So we end up with a photorealistic data-driven simulation engine that allows us to synthesize new viewpoints. And to achieve this, we simply use a recorded dataset as input and obtain, depending on the trajectory in the simulated world, new viewpoints as an output. And this ultimately allows us to perform reinforcement learning with a zero-shot transfer of the learned policy to real-world driving. The key idea of the simulator is based on looking at the image, but also at the depth data associated with the image. So for each agent, we have a state of the agent in the virtual world. We can update the state of the agent using the action obtained from the policy or from some pre-recorded data and the dynamics model of the car. And we create a correspondence between each position in the virtual world and each position in the real world, which then allows us to retrieve the image that is closest to that position and its depth map that we can either obtain from some sort of depth network or from stereo data. And using this depth map and the image from the closest location, we can synthesize a new viewpoint and fill holes by interpolation. This approach allows us to train a driving policy using a relatively simple reinforcement learning approach. In our case, we use a very simple policy gradient without any reward shaping or none of the typical variance reduction tricks. To simply demonstrate that even with approaches as simple as this, we can actually successfully learn how to drive. And here you see our ultimate driving policy driving in our testing environment. And again, this trained RL policy has never seen any human control commands. Neither has it seen any actual real-world data. It has only seen the data that has been synthesized in our data-driven simulator. Of course, other approaches can also be used to learn how to drive, but one of the main advantages of using data-driven simulation is that it is very data efficient. So we compared it to other approaches based on domain randomization, domain adaptation, and imitation learning. And the fascinating result is that for the same amount of data, our approach was more data efficient and allowed us to drive without human interventions, while human interventions were still required in some of these other approaches. But it is not only more data efficient, it also learns to recover from complicated starting positions, such as slightly being at the edge of the road or not looking to the center of the road. In all such cases, we could require successfully return to navigating safely the road, while approaches that have been purely trained on recorded data had a hard time doing this, as they might not have seen this type of situations in the recorded data set. So in conclusion, data-driven simulation enables robust learning policies without asking the drivers who record data sets to actually create dangerous edge cases for data recording. So, in summary, a lot of work needs still to be done to fully enable robust navigation and learning for autonomous systems. However, in this talk, I tried to make 2 points. First, we need to solve several new perception challenges if we want to have human-level autonomous driving. And second, perception research is useful beyond merely better understanding of the environment and can help us to come up with better driving and control policies. Thank you for your attention, and I look forward to your questions.